We start off with an example that underscores the utility of long division. We have the integral of 3t minus 2 divided by t plus 1 dt. The techniques in this section depend on us having a proper rational function. This is not proper because the degree of the numerator is not less than the degree of the denominator. Therefore, we're going to use long division, 3t minus 2 divided by t plus 1. In order to perform long division, we divide the first term of the divisor, that's on the outside, into the first term of the dividend, that's the one on the inside. 3t divided by t is going to give us 3, and then we multiply. 3t plus 3, when we multiply we distribute, and then subtract from the original dividend. 3t minus 3t subtracts out. Negative 2 minus 3 is going to give us negative 5. Therefore, our quotient is 3, and then we have minus 5 divided by t plus 1. We've transformed the way our integrand looks. We now have the integral of 3 minus 5 over t plus 1 dt. The integral of 3 with respect to t is 3t. And then we have something that's going to integrate to a natural log, right? We have a negative 5 as a coefficient, and the integral of 1 over t plus 1 dt would integrate to the natural log of the absolute value of t plus 1. Therefore, our answer is 3t plus 5 times the natural log of the absolute value of t plus 1 plus c, our constant of integration. Next, we have the integral from 0 to 1 of x minus 4 divided by x squared plus 5x plus 6 dx. We have a proper rational function, but if you tried, say, using a u substitution, maybe this will work out to be a natural log. Letting u equal the denominator, x squared plus 5x plus 6, would lead us to du is equal to the quantity of 2x plus 5 dx. In the numerator, we do not have 2x plus 5, we have x minus 4. Therefore, this attempt at a basic u substitution is not going to work. What will work is partial fraction decomposition. We'll write down x minus 4 over, and we're going to factor the denominator, x plus 2 times x plus 3. At this point, folks, when you're doing your work, even if you've got a really basic denominator, it factors in a way that's obvious to you. Just do a quick little double check, make sure you didn't overlook anything. Both of these factors are linear. So I'm going to set up two fractions, one of which has a denominator of x plus 2, one has a denominator of x plus 3. A linear denominator means a constant numerator, so our fractions are actually a over x plus 2 plus b over x plus 3. If we multiply the numerator and denominator of the first fraction by x plus 3, we get a common denominator with the expression on the left-hand side. And then the second fraction we would multiply by x plus 2 over x plus 2, and again achieve a common denominator now throughout. Once we have that, we're going to focus on the numerators. I will form an equation of the numerators. X minus 4 is equal to a times the quantity of x plus 3 plus b times the quantity of x plus 2. At this point, we could go two different ways. One of them is to multiply on the right-hand side and collect our like terms. Distributing a into x plus 3 and b into x plus 2, and then collecting our like terms, will give us a plus b times x plus 3a plus 2b. That's equal to x minus 4. Equating coefficients of like terms on the left and on the right, since on the left we have a single x, and on the right we have a plus bx, we would know that 1 is equal to a plus b. On the left our constant is negative 4. On the right our constant terms are 3a plus 2b. Therefore we can say that negative 4 is equal to 3a plus 2b. We now have a system of equations. 1 is equal to a plus b, and negative 4 is equal to 3a plus 2b. We can solve that system. That's one of the two ways we can go about this work. The other way is we have here on the right-hand side a times the quantity of x plus 3 and b times the quantity of x plus 2. If we pick strategic values for x, we can zero out the a term or the b term as we want. If we suppose that x is equal to negative 3, and everywhere in that equation we put negative 3 in place of x, we will end up with the equation negative 7 is equal to negative b. That'll tell us that b is equal to 7. If we were then to pick negative 2 in place of x, we would zero out the b term on the right. And so if x is equal to negative 2, again, we're substituting everywhere we see x in the equation, we would end up with negative 6 is equal to a. And we have found a and b. A was the numerator of a fraction that had a denominator of x plus 2. So I have a fraction negative 6 over x plus 2. B was the numerator of a fraction with a denominator of x plus 3. And so I have a fraction 7 over x plus 3. Before I continue, at some point during all of this, you may have wondered what would happen if you had written down your first fraction as a denominator of x plus 3 and your second fraction was a denominator of x plus 2. In other words, was there anything that told me that I needed to put x plus 2 as the first denominator? The answer is no, there wasn't. It's just what I chose to do. If we had these reversed, you and you had a over x plus 3 and b over x plus 2, that would be totally fine. We'd have different values from each other for a and b, but when we put them back together as our fractions, we would still have the same fractions, you and I would. Now this set of fractions, negative 6 over x plus 2 plus 7 over x plus 3, replaces the original integrand. Therefore, we now have the integral from 0 to 1 of negative 6 over x plus 2 plus 7 over x plus 3 dx. And it's that we're going to integrate now. In both of these cases, the denominator x plus 2 and x plus 3 have derivatives of dx, if you're thinking about a u substitution. So our fraction decomposition leads us to integrals that will lead us to natural logs. In other words, our answer is negative 6 times the natural log of x plus 2 plus 7 times the natural log of x plus 3. We're going to evaluate all of that from 0 to 1 because this was a definite integral to begin with. And you may be wondering, what about the absolute values? Well, because the inputs are going to be 0 and 1, I know that the arguments will never be negative, so I'm not bothering with the absolute values. We're going to end up with negative 6 times the natural log of 3 plus 7 times the natural log of 4. That's what happens when we replace x by 1, minus negative 6 times the natural log of 2 plus 7 times the natural log of 3. That's what we get when we evaluate the expression at 0, the lower limit. Now, 7 times the natural log of 4 can be expressed as 7 times the natural log of 2 squared, which can then be expressed as 14 times the natural log of 2. I only care about that because we also have a 6 natural log of 2, and I'm going to combine my like terms. When I do that, 14 times the natural log of 2 minus negative 6 times the natural log of 2 becomes 20 times the natural log of 2. Negative 6 times the natural log of 3 minus 7 times the natural log of 3 is negative 13 times the natural log of 3, and that's sufficient as a final answer.